Imagine floating through deep space toward a massive gravitational monster, where a glowing accretion disk bends light around an absolute pitch-black sphere. As you draw closer, your instruments register spacetime warping beyond anything known to physics, and you reach the event horizon, the ultimate point of no return. What actually happens if an observer crosses this invisible threshold? What would you see, feel, and experience as you plunge deeper into the black hole? For over a century, scientists believed that crossing the event horizon meant instant annihilation inside a mystery black abyss. Yet today, verified by supercomputer general relativity calculations at Caltech and NASA, astrophysicists can map the precise mathematics of the interior. How do space and time swap roles beyond the horizon? Why would looking back allow you to witness the future of the entire outside universe? And what lies at the ultimate center, a zero-volume singularity, a spinning Kerr ring, or a quantum holographic boundary? Today, we embark on an extraordinary mind-bending journey to discover what really happens inside a black hole. Our journey begins with Albert Einstein's 1915 general theory of relativity, which proved that immense mass warps the geometric fabric of space and time. Physicist Carl Schwarzschild solved Einstein's field equations, discovering that if mass is compressed within a specific radius, gravity becomes infinite. Surrounding every black hole at 1.5 times the Schwarzschild radius lies the photon sphere, a region where gravity is so strong that light photons orbit in endless circles. If you were positioned at the photon sphere and looked sideways, you would literally see the back of your own head, as light emitted from your body travels around the black hole. As you fall past the photon sphere toward the horizon, intense gravitational time dilation takes over, as predicted by Einstein's relativity. To an observer watching safely from far away, your clock would appear to slow down endlessly, your image fading into a dark infrared redshift. To the distant viewer, you would seem to freeze forever at the horizon, never quite falling in, yet from your own personal perspective, time flows normally as you cross. At the moment you cross the event horizon, nothing local dramatically explodes, yet the fundamental laws of geometry undergo a mind-bending mathematical reversal. Milestone 1, the mathematical inversion of space and time inside the event horizon. Outside the black hole, you have freedom to move in any direction in space, forward, backward, left, or right, while time relentlessly moves forward toward tomorrow. Inside the horizon, the mathematical signs in Einstein's metric flip, the radial spatial coordinate becomes timelike, and time becomes spacelike. This means moving inward toward the central singularity is no longer a choice in space, it becomes your inevitable future in time. Trying to fire rocket thrusters outward inside a black hole is as futile as trying to travel backward into yesterday. Milestone 2, extreme tidal spaghettification and viewing the future of the universe. As you plunge deeper, gravitational gradients escalate violently. The gravitational pull on your feet becomes millions of times stronger than on your head. Tidal forces stretch your body vertically into long streams of atoms while compressing you horizontally, a phenomenon known as spaghettification. Simultaneously, looking back toward the event horizon reveals an extraordinary optical distortion. Light from the outside universe concentrates into a bright shrinking disk above you, sped up by extreme time dilation. In your final seconds, you would watch the entire future history of the outside universe, stars dying, galaxies colliding, unfold before your eyes like a fast-forward film. Milestone 3, the Singularity Core, Kerr rotating ring, and the holographic boundary. At the center of a static Schwarzschild black hole lies the singularity, a point where curvature becomes infinite and known laws of physics collapse. However, real astrophysical black holes rotate rapidly. In a spinning Kerr black hole, centrifugal forces smear the singularity into a ring-shaped portal. Theoretical physicists like Kip Thorne and Juan Meldacena proposed that rotating ring singularities could form Einstein-Rosen bridges, wormholes connecting to parallel realms. Furthermore, the holographic principle formulated by Leonard Susskind suggests that all information falling into a black hole is encoded on its 2D horizon surface. Understanding the interior of black holes is the ultimate frontier, uniting general relativity with quantum mechanics into a unified theory of quantum gravity. The ER equals EPR conjecture suggests that quantum entanglement between particles is physically equivalent to microscopic wormhole bridges weaving space together. Far from being simple cosmic vacuum cleaners, black holes are the fundamental engines shaping galaxy formation, entropy, and spacetime architecture. As astronomer Carl Sagan famously observed, we inhabit a universe where mysterious abysses challenge us to expand human consciousness. Every secret decoded inside a black hole brings humanity closer to answering why the cosmos exists and how space itself was born. Thank you for joining us on this exploration of what happens inside a black hole. Farewell, and see you on our next voyage into the mysteries of space. Supercomputer models at Caltech confirm that gravitational deflection near the event horizon creates complex photon orbits. The photon sphere marks the absolute boundary where unstable circular orbits of light rays can exist. Gravitational redshift stretches light wavelengths entering the black hole toward extreme infrared radio frequencies. Schwarzschild coordinates break down at the horizon, but Kruskal-Zakhary's coordinates reveal a smooth spacetime path for infalling observers. For supermassive black holes like M87*, tidal forces at the horizon are surprisingly gentle, allowing an astronaut to cross unharmed initially. Inner Cauchy horizons inside Kerr black holes create mass inflation instabilities where quantum energy density surges to the Planck scale. Traversable wormholes require exotic matter with negative energy density to hold the throat open against gravitational collapse. Black hole entropy scales with event horizon surface area rather than volume, discovering the fundamental limits of information density. NASA and EHT visualizations continue refining our understanding of accretion dynamics around central singularities. Human curiosity transforms mathematical equations into vivid windows revealing the inner workings of our universe. Relativistic jets launched near spinning black holes propel matter at 99% the speed of light into deep space. Future space observatories like LISA will probe spacetime ripples emitted during extreme mass ratio in spirals into black holes. Quantum loop gravity proposes that singularities are replaced by quantum bounces, preventing infinite density collapse. Deciphering black hole interiors remains humanity's greatest quest to unify quantum physics with gravity. Rotating Kerr black holes create an ergosphere outside their event horizon, where rotational energy can theoretically be extracted via the Penrose process. The cosmos continues to surprise us, proving that reality is far grander than our boldest dreams. Until our next deep space journey, keep gazing upward into the magnificent cosmic expanse. Every boundary we cross in physics brings us closer to understanding the true origin of space and time. The mystery of black holes will inspire generations of scientists to push the boundaries of knowledge forever.